Okay, so now we're back to our original problem, and we're armed with everything we need to solve it. So break f1 into components and write out expressions for f1, fy, fx. Well, we just did SOHCAHTOA and the Pythagorean theorem. So how are we going to break it into components? So let's isolate f1. What does f1 look like on a right angle triangle? It looks like the hypotenuse, right? And then fx, I keep saying f of x. fx is the x component of f1, and that is along the x-axis. And fy is along the y-axis, and that's the y component of f1. So how do we write an expression for this? So f1, we could write an expression for no problem, because we know the Pythagorean theorem is a squared plus b squared equals to c squared, right? And this being the hypotenuse and also c in our formula, we can just easily do that, right? So let's write an expression for f1. So using a squared plus b squared equals to c squared, we know that fx squared plus fy squared is equal to f1 squared. This is how we find magnitudes for our vectors. So now solving for f1, you take the square root of both sides and you get this f1 is equal to the square root of fx plus fy. That's it. That's your expression for f1. Now let's do it for fy and fx. And I'll give you a hint, it has nothing to do with the Pythagorean theorem. It has everything to do with SOHCAHTOA. So, fx is equal to what? Recall there's an angle right here. Where's f of x? Where is fx relative to that angle? It's adjacent, right? So given that it's adjacent, and we have f1 here to use, we're definitely going to use sine. Definitely. Sorry, cosine, because it's adjacent. And remember, SOHCAHTOA, cosine is adjacent over hypotenuse. So to do this, we need the magnitude of f1, cosine of theta. And that is our component fx. Now for fy, we know that it's opposite, so we're definitely using sine, because opposite over hypotenuse, so we get the magnitude of f1 times the sine of theta. And you might be confused because our triangle, when we did the right angle triangle, we had something that looked like this, right? Sine of theta is equal to opposite over hypotenuse. And this is looking a little different. But if we just solve for opposite, then it looks pretty similar, right? Opposite is equal to h times the hypotenuse times sine of theta, right? So let's go back to our components here. So we have sine theta. What is the opposite of sine theta? It's fy, right? Across from it. So let's put fy there. And the hypotenuse, of course, is f1, the magnitude of f1. So we want to write an expression for fy. So let's solve for fy. So multiply f1 on both sides, and we get f1 sine of theta is equal to fy. And there's your expression for fy. And you can do the same thing with fx. Now, here's a bonus question. Write an expression for theta. Write an expression for theta. How would you do that? Using these components. Well, you can do it many ways. We remember how we said, like, you can just do the inverse cos, but you should remember that if you don't have f1, you can use these components. So the inverse tan of opposite over adjacent is theta. So theta is equal to tan inverse of opposite fy over fx. And that is all you need to know for physics with trig. You could benefit from knowing the law of parallelograms and the sine law and the cosine law, but to be honest, you rarely use it, and you mostly just find the angles like this. But I'm going to make a video on the sine law and the cosine law, so if you need that, be sure to watch that. I hope you enjoyed this video. Thank you for watching. Subscribe if you want more content from me. Don't subscribe if you hated this video. Please tell me how bad it was, because I don't have a lot of videos out, and I just want to know what I'm doing wrong, what I'm doing right. So have a great rest of your day. Watch some more of my content, please.